Happy to be here today. And I'm Velmira. I'm AI engineer, part of SAP, and this is my co-speaker, Ross.
Hi everyone, I'm Ross. I'm a principal software engineer at Broadcom's Enterprise Security Group. For those that don't recognize this name, it's basically Symantec and Carbon Black. Right, so it's 3 a.m. and a lot of previous speakers actually talk about that, but it's 3 a.m. and you're just woken up. What would you like to have? Would you like to spend about half an hour investigating possible issues and trying to figure out what the problem is and trying to come up with a fix? Or would you like to have a ready-made solution that just needs your review and approval?
So, agenda for today, we start with our architecture and show you how the SRE bot AI agent works in practice. Then we continue with engineering the context, and in this part I will show you what happened inside in the agent, then continue with our demo and wrap up by lesson learned. Let's start simple. This is our order services application. A standard Go microservices running in Kubernetes. Here we have 2 pods, cluster IP service and mount secret. So let's continue with architecture.
Yeah, so we do have our ordering service running on our workflow Kubernetes cluster here. And what we want to come up with is an SRE bot that would help us monitor and troubleshoot this service. We do have the tried and trusted Prometheus and Alert Manager. So whenever Prometheus detects a problem, Alert Manager is used to send a message via this alert bridge, which is a simple deployment, very simple Python script which translates the alert from Alert Manager's code to a message in one of our instant messaging applications. In our demo, we actually use Discord, but you can use Slack, Teams, whatever you like. You can also use PagerDuty or other incident management platform. We then use OpenClaw and some MCP servers together, running on the OpenClaw Kubernetes cluster, which is a separate Kubernetes instance, to troubleshoot this alert. Basically, we do use the OpenClaw Kubernetes operator, which we highly encourage you to use if you are going to deploy OpenClaw on Kubernetes. What we do have here is OpenClaw monitoring the instant messaging application, trying to get the alert in question, and then using one of the LLMs, which are available out there, to process that alert along with information from the MCP context to get to troubleshoot it and figure out a possible solution, and even to send a pull request to one of our source control systems. In our case, that's GitHub. The MCP service in question that we actually use for this demo are a Kubernetes MCP server, which is used to fetch stuff from the Kubernetes cluster, and we also use the GitHub's hosted MCP server for source code access of the actual service, Git history, issues, whatever. Okay. So I can probably show you the YAML, the boilerplate out there, but that's probably not going to be too interesting. What we want to show you in particular is basically 3 things: security, protection, and engineering the context. Let's start with security. Basically, this is all about securing your OpenClaw deployment and your chat with it. As you probably know, OpenClaw is pretty easy to hijack, so keeping things secure and straight here is very important. Protection is about protecting your environment from a rogue agent itself. So, for example, should your agent decide that for some reason it wants to destroy your production environment and rebuild it from ground up, that's probably not going to be a good idea. So that's something we need to think about, and we shouldn't empower the agent with capabilities that it shouldn't have. And finally, and probably the most important part of this talk, is engineering the context. On this slide, I'm going to talk about 3 things, but these are actually 4, and Velmira will continue on the next slides about the 4th one. The first one is the system prompt. Basically, this gives you the frame in which the agent is working. This gives boundaries that shouldn't be crossed in any normal circumstances. Second one is the skills. Basically, the skills are, in our case, a run book, so to say. That's basically a set of recipes that combine together different tools to which the agent has access to tackle some different problems. Also, it defines a set of workflows, which are more or less step-by-step guides for the agent on how to tackle different problems and how to perform different tasks. And last but not least is the invocation prompt. This is basically the prompt that's being used by either humans like us, typing in the Discord chat in our case, or by some sort of machinery, like the alert manager via its alert bridge. Basically, this prompt is really important in order to get things right. And how that's exactly done and will be shown by Velmira in a moment.
So, it's 3 AM, and suddenly you get an alert, and you start entering prompt manually, just like most people would. You type the first that come to mind. Check the pods, check log, namespace, no filtering, just scan the entry cluster. In an automated environment, these messages are actually the system prompts and summarization prompts embedded in the bot configuration. But to be honest, this is the worst possible prompt. Why? Do you see the context bar? The agent consumes about 14,000 tokens to process your request. What means that? You lost the model's ability to reason because noise clogs the signal and gives a wrong diagnostics. The prompt defines the agent's context. When an AI agent investigates a problem, it works within a context window. That's its working memory. Here you can see an example of the context window like a box. Every tool calls adds a data. On the screen, you can see the number of tools being a code. At a certain point, we start adding a noise into our context, showing orange. And so after n calls, half of Windows is full and most of it is noise. The context window stopped being an asset and became a problem. What's the agent actually doing? Let's look at step by step. Here, I'm using a custom tool, but if you want, you can wrap up. At the end of the presentation, you can see the QR code for that. I use this tool to keep things simple and visible, but what I'm about to show applies to any MCP-based agent, including what you will see in the full demonstration later. So let's start with connection, our agent. Okay, so connect to our MCP server, and here you can see we have 23 tools. And then we start the pulling data from pods, from events, from log. Continue with deployment spec, pod description. Each MCP call adds a real cluster data to the context window. And after the 6th call, we are at 10% of the context window. But in production, the agent doesn't stop after the 6th call. Maybe after 16, we don't know. But with every step, we will be filling up the context window. And with the Kubernetes continuously restarting a pod and recovering stage, every restart introduces fresh walk and execution the context. Further expanding the amount of the context carry over the time. And here is the critical point. Context, it's not longer helping us. Most of those tokens are duplicated logs line data the agent has already extract signal from. The context window is filling with noise, not with knowledge. In practice, this is called context explosion. This noise from unnecessary data start causing hallucinating the LLM. How we solve the problem? We need to compress. We send all tokens to LLM as a structured summarization prompt, extract unique error. The summary captures the one unique error, everything the agents need to reason about the problem fits in a single JSON block. And this is the key idea. Carry knowledge, discard the data. We extract the signal, we compress it, and now we hand off a clean 225 tokens summary to the next reasoning step. This is what a context engineering means in practice. It's not about having a bigger windows. It's about being disciplined about what we say, what we stay in. Maybe you're thinking what happened with incompletable context. Let's see. The agent gets log only, no deployment spec. Okay. It spots the error. It knows it's a missing config file. It event catches the pod inconsistency. But look, it tells you what it can determine it. Missing mount, wrong path, it doesn't guess. It asks for the extract kubectl commands it needs. And let's add the deployment spec. Okay, here we have the same model, same agent, but this time it gives you the root case, the evidence change, and the end copy-paste fix. The model didn't get smarter between those two calls. We give it a better context. That's the whole point. Context engineering, not prompt tricks. All right.
Okay, so you learned about engineering the context. You put together all of the necessary YAMLs, all of the Python boilerplate, and we're ready for our first test. In here, we do see two windows side by side. So on this side, we do have the Discord chat with our SRE bot. And on the other side, we do have the GitHub page that's hosting our source code for the order service. Now on this setup, we don't have it yet fully automated. So basically, the alert manager won't attack directly the SRE bot. You can see that the tag here is disabled. But what we are going to do is try to type in some invocation prompts and see what happens. So the alert manager has just put in the alert there, and we manually create a thread. We tag the @SRE bot and say, please investigate this alert. And as you can see, the SRE bot is thinking, sort of, and it outputs something here. And you can see that on the left side, we do have the issue created on GitHub. But this was something simple that it should have been able to fix by itself. So it should have been able to open a pull request. And if you look on the pull request page, there is nothing in there. So what happened really quickly, please investigate this alert. That's our prompt. The alert was investigated, but no pull request was created. So let's try and force him to do so. Continuing from where we have left, we again tag the SRE bot and say, please strictly follow the GitHub project workflow to fix this alert. And as you can see, it's rolling in again, and within just a few seconds, we'll have our pull request. And if we go on the left side, you can see that the pull request is going to show up on the refresh. You can see it's tagging the proper issue from our previous run, and we do have the changes necessary to fix this problem. So what happened? Basically, we had to follow up with this prompt, which is please strictly follow the GitHub project workflow to fix the alert, and that got us a pull request. But why was that actually needed? Well, if you go to your human colleague and tell him, please investigate this alert, you would assume that he would actually get to also fix it. And they would also assume that they would pretty much are expected to fix it. But that's not the case with agents. With agents, you explicitly have to tell them to go and fix the alert, not just investigate it. So in fact, in order to get our agent doing what we want him to do, we need to combine both prompts together. So let's see how that's done. Again, the same setup, but this time we're only spectators. We're not going to type in absolutely anything. We're going to just see what happens once the alert manager posts the alert. So you can see the alert is posted. We do have the thread created automatically, and the bot is tagged in it. And it's already processing the alert. And as you can see, we do get a response here. And here you can see that we do have the alert summary, we do have the context tracking, we do have our findings, evidence, likely cause, and links to the issue and the pull request. So if you go on the left side here, we'll see we're still at the issues page. If we go on the left side, you'll see that the issue is popping up. It does have more or less the same information as on the side in here. And you can also see that the pull request is itself also created, and we have the proper issue tagged, and the change is also implemented. Now, this is actually sped up here, but basically it's 52 seconds from alert manager posting the alert to the SRE bot posting the pull request link. So that's how fast it is. It is impressive, and most importantly, it's working, more or less. Okay, so lessons learned about engineering the context. It's really important to remember these three things. First, you should track your context size. Basically, if you put too much stuff in your context, first of all, you're going to pay more at the end of the month because you're exhausting more tokens. Second of all, you're probably going to run the risk of filling up your context to the brim, which can cause your model to hallucinate. And that's not something you want to have at 3 a.m., let's face it. Then you have to vet your agent skills. Like this example uses OpenClaw, and a recent study actually showed that about 20% of all agent skills that are ready-made on the internet for OpenClaw are actually malicious ones. So they are designed to exfiltrate sensitive data from your environments. That's why it's really important to have your agent skills vetted by someone line by line. Like, you need to know what's in there. And what is even better is for you to basically design your own agent skills. That way you can finely tune them for your own environment. And you should probably use the exact LLM model, or even slightly better one than the one that you're using for OpenClaw, to design those skills. Simply that in that case, you would be able to, the LLM that's running in the agent would be able to more easily pick up on those, on the knowledge of that's encoded in those skills. Choose your invocation prompt wisely. We talked about that. You can blow up your context. You can make the SRE bot useless. You can like screw up in a lot of ways here, even if you designed your skill set and system prompts well. About deploying OpenClaw itself, there are a few things to remember. The first one is secure your chat with OpenClaw, obviously. You need a private chat room with it. You need only a set of allow listed personnel who are able to talk to it. It shouldn't be able to be DM'd in any way, and it should only respond when it's specifically tagged. About securing your deployment of OpenClaw, OpenClaw can expose up to 2 ports, and if by some huge misconfiguration, some of those ports are open to the internet, you'll get hacked with your environment hijacked within just seconds nowadays. So you need to make sure that your OpenClaw ports are closed or not accessible to anyone who shouldn't access them. You need to choose your model wisely. Like going for a cheap model is okay, but it's probably not going to work in a lot of the cases. Cheap models also have smaller context, so filling up the window there is really easy, and that would get us into hallucinations. Going with like more expensive model, on the other hand, can produce spectacular results. It does have like a larger context, but it can also produce spectacular bill at the end of the month. So probably you should go with a solution that's somewhere in the middle. But yeah, you need to try and test it to see what works for you the best. And the final and probably most useful for your bill is disable heartbeat messages. So basically, OpenClaw has this enabled by default. So every 30 minutes, it will just message the LLM and say, are you still there? And the LLM would respond with, yeah, I'm still here. And that with GPT 5.5 on the current prices gets us at about 20 cents per such call, which gets us at $10 per day and about $300 of wasted money per month. So that's something that you need to disable. Trust me, we found out about this the hard way. About the MCP servers, 3 main things. First of all, you need to prefer like hosted MCP servers. So for example, if you're running stuff on a cloud, you should probably prefer to use the MCP server that's exposed by your cloud provider. And in our case, actually for this demo, we do use the GitHub MCP server. That way, we don't have to think about deployment, security fixes, and all of this kind of stuff. You just leave it to the person that's providing the SaaS to you. But it is perfectly okay to use also self-hosted MCP servers. Like in our case, in our demo, because we are hosting our own Kubernetes clusters. In that case, we did have to deploy our own Kubernetes MCP server. And we need to protect those as well. Their ports should be not reachable to pretty much anyone else but the agent itself. And in fact, what we actually did is manage those MCP servers using the OpenClaw Kubernetes operator. And we put them as sidecars to the agent itself. And in that way, we were able to tell him the MCP servers to listen to the local host only. So basically, nothing outside of the pod should have been able to access them. And last but not least, regardless of whether you're using self-hosted or someone else's hosted MCP servers, you should make sure you give them less capabilities as possible. Basically, your agent is something like a junior developer, a very smart one, but you shouldn't entrust your junior developers with the admin access to your production environment, should they decide to delete it for some reason. And yeah, in our case, with the Kubernetes MCP servers, we decided that it's probably best to give read-only access, but you can probably also give some write capabilities, like really tiny ones, like basically being able to restart some deployments, put together port forwardings and stuff like that. Probably some scaling as well. And for GitHub, the GitHub MCP server, there is crucial not to give write capabilities like too much. The only write capabilities we gave our MCP server were like being able to create issues, pull requests, and comments. In particular, you shouldn't allow them to merge any unreviewed pull requests, and you shouldn't allow them to execute any CI pipelines. And with that, the overall conclusion, the SRE bot is really nice to have, especially at 3 a.m. I know you've been hearing about that time frame a lot today, but yeah, in the end, we do have to have humans in the loop. If we don't, probably we're going to end up in some sort of disaster. And with that, some questions?
Before that, thank you.